Okay, so let's go ahead and move on to this next theorem. Let's suppose that capital F is a vector field and it's continuous on an open connected region D. So we've defined open and connected now, so we can kind of visualize what that looks like. If the line integral along C of f dot dr is independent of path in D, then f is a conservative vector field on D. That is, there exists a potential function, lowercase f, whose gradient is equal to capital F. Okay, so we have a couple of pictures that accompany this and one more down here that you'll see in a moment. And just to point something out, even though this region looks like it includes its boundary, our assumption here is that this is an open connected region, so that it actually does not contain that boundary despite what it looks like. What we're going to try and do here is take this assumption that this line integral is independent of path in this region D, and use it to construct a potential function for f. This is a proof by construction where we actually try to create the thing that we're looking for. So what we do is we pick any just arbitrary point in D and call it AB, and we define a function of x and y in terms of this. Now, we haven't used this notation before. This looks like a definite integral, but you notice that the lower and upper limits are ordered pairs. So this may be a little bit confusing at first, but what this means is that we're looking at a line integral, not a definite integral, but a line integral where the curve that we're integrating over is just any path connecting AB as its initial point to xy as its terminal point. So in the image here, you can see AB was chosen down here, and xy is this point up here. And so the line integral is just integrating this path or any other path with this as the initial point and this as the terminal point. Okay, so again, not a definite integral, that's a line integral, despite what the notation seems to say. Now we made the assumption that this is independent of path, so it doesn't matter how we get from here to here, this line integral should always come out to the same thing under that assumption. Because D is open, we can put this, we can put a disk centered at xy in D. So that was the definition of this being open. We can find a disk centered at xy such that the disk is entirely contained in D. What we're going to do is pick a point that has the same y coordinate as this point xy and is also contained in this disk. Okay, so that means that these 2 points can be joined by a horizontal line segment if their y coordinate is the same. And what we're going to do is build this path, some path C1, and this path, it doesn't matter what it looks like, it's just going to connect the point AB to the point x1y, and then this path C2, it does matter what this looks like. It's going to be a horizontal path going from x1y to xy. Okay, so we've constructed this path together. C1 and C2 go together to make the path that takes us from this initial point to that terminal point. So I would think of that entire thing as C. All right. If we wanted to evaluate the line integral, f dot dr along this path C, the one that joins these two paths, it would be the same as the sum of the line integral along this path plus the line integral along this path. That's what we're seeing right here. Okay. Now, using the notation that we used up here, I could say that the line integral along the path C1 takes me from the initial point AB to the point x1y, and these 2 points in the path itself are all contained in D, where everything is independent of path. So it makes sense to use this notation. And I'm not going to do anything special with the C2 quite yet. But notice, if I were to take this line integral, which I'm defining as the function f of xy, and I know this part can be a little bit confusing, but this is actually a function of x and y because different choices of x and y determine different points that we're picking in this region D to be our terminal point for our line integral. But the way that I chose this point, notice the x1 is a constant. So really, I would think of this as the function f of x1 y if I were only looking at this integral. This integral does depend on x, but this one doesn't. The fact that it doesn't depend on x means it's really just a function of y. This x1 is being held constant. And again, I'm only talking about this first term right here. This first term is a function of y. So if I were to differentiate, take a partial derivative of this function with respect to x, this doesn't depend on x. It would be treated like a constant and it would go to 0. This guy would just look like the partial with respect to x of that line integral along C2. Okay. Next thing I want to do is represent f. It is a vector field, so I should be able to represent it this way. And again, we're working in a plane here, so it would have two components, an I and a j component. If I gave f this form, the kind of the component form, then f dot dr, the line integral of f dot dr looks like the line integral of p dx plus q dy. We showed this in the previous section. Okay, now the reason we chose the path that we did up here for C2 is now going to become apparent. So on this path, notice the y is not changing. It's horizontal. So the y coordinate of any point along that path is constant. So what does that imply about this line integral right here? Well, if y is constant, then dy, remember dy ends up looking like y prime of t dt. Dy would just be equal to 0, so that this entire term goes to 0. And the line integral along the path C2 shrinks down to just p dx in here. So that's what's happening here. This q dy is going to disappear, and then it's just p contained in the, or p in my integrand. And then remember, this dx becomes x prime dt. So really, when I evaluate this, it becomes a definite integral in terms of t. And if you notice, I have to create what we call a dummy variable here because I've already used x and y. I'm putting a t here in the place of the x because I'm integrating with respect to t, and t is going to go from x1 to x. What that means is that t is taking us from this initial point where my x coordinate is x1 to this terminal point where my x coordinate is just x. Okay, hopefully that makes sense. Now this x here, remember, it came from the function f of x, y. It's technically a variable. x1 is a constant. So from this, from the first part of the fundamental theorem of calculus, from calculus 1, I have a function of x, and I'm taking its derivative with respect to x. That's going to give me the integrand where an x is going to take the place of this t. It becomes p of xy. Okay. So that's what this is arguing right here. Okay. Then if we did something similar, and we don't need to walk through this entire argument again, but if I did a similar thing where I constructed a path from a, b to x, y, but instead chose a point where the x coordinate, chose a point in that disk where the x coordinate is the same as x, the center of that disk, then those 2 points can be joined by a vertical line segment instead of a horizontal line segment like what we did up here. Going through similar steps, and you can sort of see the argument here, we could show that the partial derivative with respect to y of f of xy gives me q of xy, where q, again, is the j component of our vector field, capital F. So what does that actually show? Well, capital F is equal to pi plus qj, that's the component form we decided to call it, but we showed that p and q are both partial derivatives, one with respect to x, one with respect to y, of the same function, f. That makes f a gradient, because this is what a gradient would look like, specifically the gradient of f. That's what shows that capital F is a conservative vector field. It's the gradient of another function. Okay, that's probably, I would say, the most complicated proof in this section, but it establishes a really important result. Okay, we're going to follow that up immediately with another theorem, a couple of theorems actually. This one says that if we have a vector field, F equals pi plus qj, and if it's a conservative vector field, where in addition to that, we assume that these component functions, p and q, have continuous first-order partial derivatives. That means both the partials with respect to x and y. On some domain D, then throughout D we have this. This is a partial differential equation, and it states that if this function is continuous, conservative, then the partial of p with respect to y will equal the partial of q with respect to x. Okay, the proof of this is pretty straightforward, especially following up the one we just did. So making these assumptions, we're assuming that f takes the form pi plus qj. This is its component form, and we're going to assume it's conservative. And p and q have continuous first-order derivatives. The purpose of this assumption is to be able to use Clairaut's theorem. So because capital F is conservative, that would imply that it has a potential function, something that this capital F is the gradient of. So that means that both p and q are partial derivatives of another function with respect to x here and respect to y here. That's what this is saying. P is the partial of f with respect to x, q is the partial of f, little f, with respect to y. So if I took these two expressions, the p and the q, and differentiated each of them, took a partial derivative of each one of them, then these first-order partial derivatives are going to become second-order partial derivatives. Specifically, if I do a partial derivative of p with respect to y, then that's taking the partial of f with respect to x and then differentiating again with respect to y. So I have a mixed partial of y with x. Clairaut's theorem allows me to reverse the order of the differentiation here. So I can differentiate with respect to y first, followed by x. But this is the same thing as the partial of q with respect to x, which you can verify here. So that establishes this result. These two partial derivatives are going to be equal to each other. And we'll see after we get through the next theorem that this gives us a really useful way of checking whether something is a conservative vector field or not. I do want to point out this is not an if and only if proof. It says if this is a conservative vector field with continuous first-order partials, then this will be true. So what that is really mostly useful for is checking to see if something is not a conservative vector field, at least as far as we can tell from this theorem. Because what this is telling us is that if I were to take a vector field, if we were given a vector field, and if I were to find the partial of the p here with respect to y, and then find the partial of the q here with respect to x, if those two expressions were not equal to each other, then this couldn't have been a conservative vector field. So it's primarily useful for ruling out the possibility that a vector field is conservative. However, there is a converse to this theorem, a partial converse, which means that it's not true in the most general case, but for specific types of regions, the converse of this will be true, which means if this partial differential equation holds, then f is conservative. So we need some terminology before we can talk about the theorem that states that. And we're going to talk about that here. The first term is what we call a simple curve. A simple curve is just a curve that doesn't intersect itself. And this gives you an idea of what a simple curve would look like. So these two curves are simple. This one is not closed, but it is simple because it doesn't cross itself. This one is a closed curve, and it's also simple because aside from the initial and terminal point being the same, it never intersects itself anywhere else. So simple and closed, simple not closed. These two curves are not simple because the curve crosses over itself. You see it intersecting itself. Okay? We need that term to define the next one. So we have what's called a simply connected region. A region D is called simply connected if any simple closed curve, like one of these, okay, any simple closed curve in D only encloses points that are also in D. So it's easiest to understand what this means by looking at counterexamples. Look at things that are not simply closed, simply connected regions. These guys down here are not simply connected. I'll look at this one, for example. You notice that the region has this hole in the middle of it. If I put this simple closed curve around that hole, notice the curve itself is entirely in the region the orange region here, but there's points that are enclosed in this closed curve that don't belong to the orange region, namely any point that would be in that little hole right there. So one way of thinking about a simply connected region is a connected region that doesn't have any holes in it. Although I want to be careful about being too simplistic with our terminology. There's a reason why we define things the way that we do. Okay, so this theorem down here is kind of like our partial converse of the one that we just talked about. Let F equal Pi plus Qi be a vector field on an open, simply connected region D. So a simply connected region that's open, meaning it would not contain its boundary. Suppose that P and Q have continuous first order partial derivatives, and that partial differential equation that we saw up there, partial of P with respect to y equals partial of Q with respect to x. If this holds throughout that region D, then F is conservative. We're not going to prove this here. We need Green's theorem to prove this, and that's the next section. So we're going to defer the proof of this theorem until we get to 16.4. Okay? But what I'd like to do is a couple of examples where we're verifying whether or not a vector field is conservative, and in the event that it is, we want to find a potential function for that function f. So first of all, I want to use the theorem that we just talked about to verify that this is a conservative vector field. And in order to do that, the domain of my function needs to be an open, simply connected region. Well, looking at my vector field here, the components are polynomials. Those are defined everywhere in the plane. The plane, or R2, is an open, simply connected region, and you can verify that straight from the definitions. So if the domain of this is all points in the plane, it satisfies the criteria that we need in order to use that last theorem. So what then are we trying to show? Well, let's call this component function P and call this component function Q so that we know what they look like in the context of that theorem. The theorem has us checking two things. I need the partial of P with respect to y. That's the first thing. Partial of P with respect to y, you can see from this, would be 2y. However, if I took the partial of Q with respect to x, which is the other partial derivative we want, then I can see that that would also be 2y in this case. My 2 looks a little bit like my partial derivatives here, so I do be careful with that. Partial of Q with respect to x. So this means that our function is conservative because the region satisfied the criteria, or the domain, I should say, satisfied the criteria of that previous theorem, and that partial differential equation was true. So that means that this function here has a potential function. This is the gradient of something. Now we have to figure out how to find that potential function. Well, in order to do that, remember, if this is the gradient of something, then P is the partial derivative of the function we're looking for with respect to x. So if I want to figure out how to backtrack from there, I would have to integrate that function P with respect to x. Y squared minus 2x dx. Notice this would give me, with respect to x, you're going to get xy squared minus x squared plus, not c. Even though this is an indefinite integral, it's not with respect to c. Remember, our functions can have variables of x and y, and if I had a function of y here, reversing this and differentiating with respect to x, this would have been treated like a constant and it would have gone away. Notice if you differentiate this with respect to x, we get right back here. Okay, so this gives me my candidate for my potential function that I'm going to call f of xy. The problem is I don't know what this function g of y looks like. However, we do know that the partial derivative of this function with respect to y, so fy of xy, should give me this other component q. So this, if I differentiated this expression with respect to y, I'm going to get 2xy minus 2x Oh, sorry, back it up. Sorry, x squared is going to be treated like a constant since we're differentiating with respect to y. So it's actually just going to be the derivative of this function with respect to y, which would look like g prime of y. Okay, compare that to q, which is equal to 2xy. Notice we already have equality. We don't need the g prime of y. That implies that g prime of y is equal to 0, which means that g of y is a constant function. So that means our potential function that we're looking for, f of xy, is equal to xy squared minus x squared plus some arbitrary constant. And I encourage you to verify that we did this correctly by taking the gradient of this function and showing that it is this. Okay, but I'll let you do that part. All right, now that theorem that we stated before only concerned vector fields in R2. But what if we have a vector field in R3? In this case, we're asked to do a couple of things. So we're given this vector field, sine of yi plus all this stuff, okay? And we want to find, we have a curve that we've defined here. What we want to do is a couple of things. We want to find a potential function for f, if one exists, and in this case one will, and then evaluate the line integral along C of f dot dr. We'll use the fundamental theorem for this because if we can find a function that capital F is, I have this backwards actually, sorry. The gradient should be on this side. Find a function that f is the gradient of, capital F is the gradient of, then this means the fundamental theorem for line integrals would apply. So if this thing is the gradient of some function, then the derivative, or the partial derivative of that function, lowercase f with respect to x, would be this first component. So if I want to backtrack from there, I need to integrate that first function with respect to x. Integrate sine of y with respect to x. Okay? Now that would be x sine of y plus, not an arbitrary constant, but a function of both y and z. Now, notice, if I were going backwards, if I wanted to differentiate with respect to x, if this function was only a function of y and z, it would be treated like a constant. So that is going to be the most general term that I can put there. Okay? So this is my candidate for f of x, y, z, the function that we're looking for. What I would need to do now is make sure that the other two components are consistent with this. Remember, this component would be the partial derivative of this with respect to y. So let's differentiate this with respect to y. F of y, or f partial of f with respect to y, here is going to be x times cosine of y. If I differentiate this with respect to y, it's the partial derivative of g with respect to y, yz. Now, this thing should end up being equal to this thing. Okay? So I can see the x cosine of y showing up here. That must mean that this cosine of z right here is what this other term is equal to. So g, the partial derivative of g with respect to y, should be equal to cosine of z. Now, the goal here is to figure out what g of yz is so I can get a complete expression for f of x, y, z. So if I were to integrate this with respect to y now, that will get me back to g. So g of yz is equal to the integral of cosine of z with respect to y. This is equal to y cosine of z plus some function of z. Okay, remember the only two variables under consideration here are y and z, but that would mean if I integrate with respect to y, this would have been treated like a constant if I then wanted to differentiate with respect to y to get back here. Okay. All right, the last thing to do, well, it's not the last thing, but next thing we want to do, if we were to differentiate this thing with respect to z, notice if this is my function, let me back that up. Oh yeah, if I differentiated this with respect to z, g of z, or gz of yz, then I would have gotten, where'd we go? Oh, I had something worked out here and I've lost it. Where'd it go? Oh yeah, there we go. Negative y sine of z plus h prime of z. This I want to compare to my last component here. So I can see that negative y sine of z is showing up as my k component in my vector field. So that would imply, because there's no extra term up here, that h prime of z is 0, kind of like our last example, meaning h of z is just some arbitrary constant. Okay, so let's backtrack. Where did h of z come from? Well, it was this term in our function g of yz. But where did g of yz come from? It came from this expression for f of xyz, which is what we ultimately wanted. So our potential function f of xyz is equal to x sine of y plus, now we find g of yz, which we found down here, y cosine of z, plus this h of z we determined was some arbitrary constant, plus c. Okay? Cool. That's the first part of the problem. I'm using a c here. Maybe I should be using something else since I'm also using a c for the curve that we defined up here, but we'll just try to be careful. So now if I wanted to evaluate this, we've found a potential function for capital F, which means capital F was a conservative vector field all along. So if I want to evaluate this this line integral, I can use the fundamental theorem. Now, we are given this parametrization of this curve, and t goes from 0 to pi over 2. I need to plug 0 and pi over 2 into this to get my initial and terminal points. So r of 0, if you plug 0 into r of t, you're going to see that you get 0, 0, 0. Let you verify that. If you plug pi over 2 into r of t, you're going to get 1 pi over 2 pi. Again, verify that by plugging those values into here. So the fundamental theorem of line integrals says that because capital F is a conservative vector field, then this is equal to f of r of 0, oops, sorry, not 0, pi over 2, I want my terminal point, minus f of r of 0. Okay? I would have to plug these two values, their x, y, and z coordinates there, into my function up here. And this c doesn't matter. You can pick any constant you want for c and you're going to get the same thing. So let's just make c equal to 0 so we only have to deal with these two terms. If you were to do that, you would find that this terminal point here gives me 1 minus pi over 2, and then this ends up giving me 0. So then my final answer is 1 minus pi over 2. Okay, a lot of work, but that's essentially what that looks like.